you for coming to this week's think tank. Our speaker today is Alberto Rovellini. Albie will be taking questions during his talk.
Thanks, Trinity. Hi, everyone. Thanks for coming in and tuning in. For those that don't know me, my name is Albie, and I'm a research scientist here at SUFS at the University of Washington. I've been here at UW for 4 years or so now, and I've been working on this topic that I'll talk about today with a few folks for quite a few years. Some of these folks are listed here, but that's by no means comprehensive of a list. I'll talk about ecosystem caps on Alaska groundfish and what those are, what those mean. Let's see if I can advance my slides. Step one. All right. So what's happening today? I'll touch on a bit of background on what ecosystem caps are, what they do in our system, or the system that I'm most familiar with, which is the Gulf of Alaska in particular. I'll go over the research questions that we've been stabbing at for a while now, and what method we use to simulate some projections. Everything that you're going to see today results-wise is simulation work. So you'll see some results that are, all of this is a work in progress, right? So I'm really keen on questions, feedback, or anything that crops up if you're familiar with this topic. So again?
Except reach you the Atlantis model.
We'll get back to you on that. And then we'll talk about management implications and some parting thoughts. So to start, what are ecosystem caps for those that are less familiar? So by ecosystem cap, at least today, I'm going to mean an annual cap on total harvest of a set of species. There are a few examples in a couple of systems of ecosystem caps, or something that could be called an ecosystem caps. And I'll touch on those. Typically, these are applied alongside single species management. So these are not intended to be substitutive of stock assessments and single species management, or at least that's not how they're used for the most part. The examples that I'm aware of, and please chime in if you are aware of more, but there's a couple of systems that kind of look at ecosystem level yield, or multi-species yield, or multi-species MSY, or some declination of that concept, and that includes some of the offshore fisheries in the North Atlantic that are managed by the Northwest Atlantic Fisheries Organization. And it's not like there's a cap per se, but what happens, at least my understanding of what happens, is that every year they present to managers estimates of multi-species MSY, or rather ecosystem level yield, and that kind of feeds into the decision process, not so much in a structured way as a hard cap, but more as a guiding sideboard rather. In Thailand, some of the multi-species fisheries are managed under a multi-species MSY, in part by virtue of the fact that it's hard to, for data limitation, it's hard to do assessments the way that some of us talk about assessments, at least in the US. There, a couple of weeks ago, we saw. Yeah, I think so.
How do they enforce
it? It's effort based. It's yeah. So they come up with an effort based measure of multi-species MSY. Well, how it's enforced,
I know Ben's been working in that area.
Right. That's right. Yeah. Yeah.
I thought most of it was wrong theoretical.
I think. I mean, I'm not intimately familiar with that context. Yeah. So I can read up and let you know. Yeah. But I know that it's in their management plans, so it's not just a paper.
I've written a lot of management plans over the years.
Right. Well, that's a different story. So yeah, we sort of think that, and the think tank about redfish, it was really cool, I thought. And it's not like there's an ecosystem cap or anything, but there will be one example of a multi-species cap that has been looked at, simply because there's a couple of species that are part of a complex, and so there is a limit to the total catch of that complex. But what I'll talk about today has to do with Alaska and Alaska groundfish in particular. So Alaska groundfish is managed with an optimum yield cap. So I'll take a quick break to talk about what optimum yield means. It's not. It's broader than the caps. Optimum yield is a term that is. Again, this is my understanding of it. Is actually enshrined in the Magnuson-Stevens Act, and it's part of the fisheries management. I think it's defined along the lines of the amount of fish that you can remove based on ecological, socioeconomic concerns. So it's broader than
Or the best value.
yeah, the best value to the nation. I think.
This is the United States, the OY. Sorry? It's the OY.
Yeah, which is defined as pretty much anything you want.
And when somebody says,
Right. So it's a fairly broad definition, but it's what the fishery should theoretically aim for, at least. And one of the ways that this is, or that they try to accomplish this is by imposing these ecosystem caps. And today I'll be talking about caps in terms of an upper limit to catch. This is actually a range for those that care. In both the Bering Sea and the Gulf of Alaska, it's a range. But today I'll be talking about the upper limit of the range, which is what seems to come in place for the most part. But yeah, it's an annual tonnage cap on total groundfish harvest. There's two values in Alaska. There's 2 million tons in the Bering Sea and 800,000 tons in the Gulf of Alaska. And that's kind of what I'll focus on today for the most part. For a bit of history, again, for those that are less familiar, these go kind of way back. I think they were first talked about or established in the late 1980s. The way that this was done back then, or what I could trace on the topic at least, was a sum of single species MSY, in so many words, discounted by some amount to account for the fact that you can't simultaneously achieve maximum yield for all stocks, conceivably at least. So like I said, this includes all the groundfish. It does not include things like Pacific halibut, because that's managed under the IPHC. It doesn't include salmon, forage fish, or anything like that. But yeah, hopefully that gives you an idea of what these caps are. So the Bering Sea cap is a. So I should say that the intent, I think, behind these caps is for them to work as ecosystem-based fisheries management tools, right? So like these are used alongside the single species stock assessments, and what you see here are historical reconstructions of harvest specifications for the Bering Sea and Aleutian Islands. I believe this is DSAI combined, but you see the ABC and the TAC, right? And basically what happens along the line, so those bars are the stacked harvest specs for each year. I think this is not updated to last year, so it might be from 2024, but the point being that if you look at the aggregate ABC, it goes over the 2 million ton cap. In fact, pollock alone, I think in some years, right, Jim, goes beyond the 2 million ton cap. And so what happens at the council level, not just based on this cap, but based on a whole set of considerations, is that these harvest specifications are rescaled such that the aggregate TAC does not exceed the 2 million tons. That's the general idea of how this should work. And it's not like there's a formula to do that, right? It's done as a discussion, so to say. So that's what the Gulf of Alaska looks like instead. These 4 panels are, so these 3 are harvest specifications, different levels of them. So you start from the UFL, which is basically what comes out of the stock assessment in a way, right? The line is the 800,000 ton cap for the Gulf. And basically here you can see what happened back when these caps were established, right? So presumably the system back in the 1980s was fairly productive, relatively speaking, at least, and the aggregate MSY for groundfish was about 800, 900,000 tons or so, and then it dipped back up back in the what was this 2016, whatever, before the heat wave, it seems, or yeah. But it never kind of went back to those levels, right? And if anything, even back early in the time series in the 90s, the ABC, the TAC, and certainly the catch were well below the cap. So in other words, the cap was never really constrained. Nothing really in the Gulf of Alaska groundfish fisheries, and a lot of this has to do with attainment. For instance, to single out one species here, these big blue bars would be arrowtooth. Arrowtooth isn't targeted very much at all in the Gulf, or hasn't been, at least historically. And so as a product of that, the aggregate catch has been well below the cap. Right, so that's a bit of an overview of the status quo, essentially, of what the cap does in the Alaska system. So what do we look at? Where do we go with this? Obviously, one question that has cropped up over time is, what if the status quo was changed for something else? So what if you were to apply a lower value of this cap for the Gulf of Alaska groundfish fisheries? Today I'm going to talk about Gulf of Alaska only. Bering Sea has a whole different set of considerations that I'm not familiar with. This project was focused on the Gulf cap. So what we looked at was what are the trade-offs of applying lower caps on the groundfish complex itself, so groundfish biomass and catch, but also the non-target fish species. So for instance, forage fish, and I'll touch on what those species are, as well as non-target species such as Pacific halibut. What are the effects of different caps on top predator biomass? So here today I'll talk about mostly stellar sea lions and pinnipeds, some dolphins and porpoise species, and some seabirds. So kind of like, what are the broader ecosystem level implications of a different cap, or what would they be? If you do apply a cap that is constraining, can you rescale your harvest specifications such that you prioritize catching high attainment species? So for instance, gadids like cod for one, pollock, but also non-gadids such as sablefish are species that are typically attained or have been attained at fairly high levels. So you have a catch that gets close enough to the harvest specs, whereas you have other species that are not attained, for instance, because they're not targeted, maybe because their economic level is not as high as other species. And obviously, how does projected climate conditions impact these considerations? Do they impact these considerations at all? So the model that we use is a simulation model. The framework is called Atlantis. It's an end-to-end ecosystem model that basically includes the physical submodel food web. It's a food web model at its core, and then a fishing and socioeconomic model. And again, I'll talk about commercial, federal managed U.S. fisheries. It's a spatially explicit model. I'm really not going to talk about the model itself in any detail. If folks are interested, they can follow up with me, and we can talk about this more. I'll just talk about what's relevant for our talk today. But yeah, it is a simulation model, and it's a deterministic model, right? So the set of inputs and parameters that you put in will correspond to a set of outputs that you'll get out. So you have to be careful in how you parameterize it in so many words. All right, so I talked about physics. We drive this model with ROMs derived time series of temperature and salinity and water movements, so currents between all those boxes, those jagged polygons that you see there. That's kind of like the spatial unit that this model works with. There's quite a lot of functional groups, but the ones that I will mostly talk about today have to do with 19 groundfish groups, and those are the ones that are in the real world, that correspond to the species that are managed under the optimum yield cap. And all of these are modeled as age, structure, populations. That's kind of a list there on the side. There's kind of the usual suspects up at the top, so pollock, cod. You'll note that some of these are single species groups, and some of them are complexes, like the rockfishes. What else? Towards the bottom, the demersal fish. So the resolution kind of varies, but all of these, if you lump them all together, they make up for the vast majority of the catch and the biomass that is in this system. Probably miss a few species, but that's okay. That is groundfish. This is what is managed under the OI. There are salmon groups in the model, but they're not part of they're not under the cap, so to speak. How do we model fisheries in this model? So we have a lot of species. So without getting into details too much, there are 4 of these that we simulate with the sloping harvest control rule, and these are pollock, cod, sablefish, and Pacific Ocean perch. That's kind of the shape that you see on screen there. There's actually 2 shapes. That's kind of what the fisheries management plan implements for these species. The pink line, which you can only see a part of because it's under the blue line for the rest of it, is the standard sloping HCR. That orange dash line there is B40. That's 2% of B0, the red line where the fishery closes. But yeah, so you're fishing at target above B40 essentially, and then it's a slope. Pollock and cod use an alternative formulation of that, where at 20% of B0 you close the fishery, and that was, to my understanding, that was set up for stellar sea lions or predator more, but I think specifically stellar sea lions is my recollection, for species that are important forage for stellar sea lions, and that's pollock, cod, and I think there's another one that it might be Atka mackerel, but that's not a big biomass in this model, so we'll focus on these. So everything else that isn't these species is managed with, or is modeled with, a fixed F rate, which is a kind of recent average F on all other species. We take the selectivity curves from Gulf of Alaska assessments where we can, and then we have our caps that I'll touch on next. Before I do that, obviously, if you use harvest control rules, you need reference points. You can't really use reference points such as B0 or B40 or target F from the single species assessments because this is a multi-species model. So at all times, you have a whole bunch of species that have trophic interactions and that influence each other's biomass. And so we determined the internal reference points for the 4 species that are managed with the HCRs, and that's kind of what you see there. So you have fish mortality on the X, and then in the left column it's biomass, and in the right column it's kind of like a yield curve. So for B0 we use essentially the leftmost point in this left column, and mind you that B0 there you can't really compare to the B0 that comes out of the GO stock assessments, like I said, because in these models here you had F equals 0 for these stocks one at a time, but then you had all the other stocks in the model, so you have predation that influences your amount of B0. But that's what we work with for this model. Let's see what else. Yeah, the only thing that I can point out is how so for these 3, pollock, Pacific Ocean perch, and sablefish, the model's estimate of FMSY is fairly close to the FOFL from the latest assessment. FOFL is the fishing mortality at the overfishing limit. So basically, you could call that a proxy of FMSY in a certain sense. The one exception was cod, where that's been a long-lasting feature of this model. I don't know that it's a feature, but this model sees cod is a fairly high FOFL in the Gulf of Alaska compared to most other stocks, and that's just something that we can get to quad work with the model, despite the parameterization that we use is fairly close to the parameters that are estimated by the assessment itself. But yeah, that's where we're at. So that was kind of an aside to kind of show you how the HCRs are parameterized. Yeah.
This is great. I think it's unusual that the cod catch levels are so low. That's I mean, it seems like all the other things are kind of ballpark.
Yeah.
What you'd expect. Is that bottomland sablefish? Is that?
Yeah.
Kind of ballpark. But
Yeah.
it seems like compared to all the others, cod catch, maybe SSB seems low.
Yeah, no, you're right. It's so those are thousands of tons, and right. So ballpark is kind of what we shot for with this model. I think that cod is a little or a lot, I'm not sure, underproductive in this model, and I'm not entirely sure why. There's a lot going on, right? You have to kind of try and get recruitment right. And get the biomass in the right ballpark. I was having a look at the biomass estimates out of the assessments for B0. That's about half what the assessment says for adult SSB. And like that's stuff that you solve by retuning the model iteratively. And that's something that we might try and address. We used to have the opposite problem. Cod used to be like a little too high, and then we modified this model in a few different ways that I'm not going to go over today. And now, now we might have undercompensated a little bit. But when you run this model with all the species at an F that is comparable to the real world fishing mortality, they all sit kind of in the ballpark biomass that we see at least from assessment estimates.
Yeah, it just, OFL is an FMSY proxy, which is at 35% for all these stuff.
Yeah, which is about where that gray line, I didn't specify, but that gray line there is, I forget if it's B35 or B40 now. So I was shooting for my biomass curve to kind of intersect that B line more or less at the, what is this, the blue line. And for cod it kind of does, right? Is so as far as the model is concerned, that's consistent. That's just not what the single species assessment says. If that makes sense. Yeah, so anyway, happy to chat more about this, but I'll move on for now. So there is only one thing that I will say about the Atlantis model itself, just because it's important in the results that you're going to see today, which is how we wire temperature effects into the model's biology. We do that in quite a few ways, but these are the key four explicit ones. So you only see 4 species depicted here because this is an old figure, but that applies to all the stocks that we have in this model. There's thermal limits to movement and spawning. Basically, you can say this, you know, based on the thermal range that this species is known to occur at, you can limit them from moving to and from a certain spatial box, or you can prevent them from spawning in a certain box if conditions get outside their spawning range. That's important for cod, which is a known stemathermic spawner, I think is how you say, but basically eggs don't hatch if it gets over a certain temperature. So that's one way what to, and then we link temperature to consumption and growth, and those are kind of like those dome-shaped curves. Forget about the dashed lines. Those are those dome-shaped curves that you see there. Basically, you say there's an optimum temperature where, and this is from lab studies, right? There's an optimum temperature where growth is maximized, and then beyond that temperature, it declines. So these are ectotherms, right? So like their metabolism increases up to a point, and then kind of comes crashing down. And then the last one that is not in the plots here, but there is a response to of respiration. So the more the warmer it gets, the more respiration increase. So that's the catabolic effect on metabolism, and what you see there is kind of like the anabolic effect, if you will. Okay, so keep that kind of like back of your brain later on, but I'll remind us. All right, so okay, all that being said, we use this modeling projection. So we projected from 2020 to end of century, because that is what we have ROMs for, and we could argue on how, you know, meaningful end of century projections are, but you know, this is a way of understanding how the system may respond to a given scenario. So you're looking at counterfactuals, in other words. You're not really forecasting or anything like that. Okay, so these are the CAP values that we apply. So we have the status quo, so the 800,000, and then kind of scaling down 200,000 tons at a time. And these aren't really meant to be options that management should consider per se. They're more to be intended as bookends to see how the system bends when you apply it to different kinds of pressures. What happens when you have a cap that does constrain your catch? So you have to decide what happens when you go from harvest specification to actual catch. And I tested 2 different ways of doing that here. And that's kind of like a schematic that illustrates it. So imagine that you have your harvest specifications that combined exceed your cap, right? And you need to comply, so you need to rescale down. And one way to do that is to do that equally for all your stocks. So basically you say that all stocks are at equal value or are attained in equal measure. So you just rescale by however much you need to fall under the cap. That's one way that you could do it. Something that is maybe closer to a conceivable process is to do that based on attainment, right? So same situation. But imagine that of those 4 species, you have 2 where you really want to keep your attainment high. So you say you want to catch them as as close as you can to the single species harvest specifications, so like the deep blue here and kind of the orange there. And then you have 2 other species that you're not targeting or are not as valuable to the fishery for whatever reason, so you can kind of sacrifice those. Okay, I'll keep going just so we carry on here. If people online cannot see, just speak up. But I think we should be back on track. Okay, so that's kind of what goes on with the.
The attainment-based one, is that the formula? Remember we talked about this workshop.
Yeah.
It's still the same.
Yeah. And I can.
Because we good to get some feedback on that. I mean, we've knocked it together quite quickly and it satisfied criteria A, which is it works.
Yeah.
But it'd be interesting to see what people think about how we actually got there. Because that's.
Yeah. Well, that was in the thing that I was trying to share my screen for. So folks online could have seen it, but folks in the room not, for reasons that I don't completely understand. But basically, the way that works is it's just.
I think I created.
Yeah. Well, unfortunately, I don't have now the formula on screen because there was a page in the app. But I can probably make it happen if we were really bent on that. But it's a fairly simple way of doing it. Like all that it does, it just needs to satisfy the condition that you can't. Well, you obviously have the constraint of the cap, and then you can't catch more than your harvest specification said. So your catch can go beyond your harvest specification. So yeah, that's probably all I'm gonna get to.
There was also a power in there, wasn't there? Or did you? It was like the power of the difference or something like that. Just trying to remember what it did. Because it would be good. Because obviously, if you're a reviewer, you want to look at that. That's sort of
yeah.
But it is consequential, as you'll show me later on.
Yeah. Well, why don't we do this? Why don't I move on, and then when we get to the end of this, I'm gonna try somehow and share that page that I was trying to share.
I think if the issue is if online they can see it, like there are enough laptops, so I don't mind going there so we can see it like online.
Okay.
Later.
Okay. Yeah. That's a good idea. We can do that. Thanks. All right. So anyway, that's kind of like the basic idea behind it. We can get into the details at the end if we have time. Climate-wise, we look at no historical conditions, so kind of like a control case where you entail no change in the environment, and then 3 increasing emission scenarios. All right, I'll step through some results, and I kind of organize them at levels of total groundfish complex, and then single species, and then total ecosystem. All right. So stepping through this, what you see here is a plot with a bunch of panels, and there's a total groundfish biomass at the top and total catch at the bottom. Basically, the colors of the lines are the cap. And is it possible to minimize that just for the folks on the room?
Yes. So I'm not going to be able to see if anyone has their.
Oh,
hand raised.
yeah, I see.
If you have a question online, please unmute yourself because I won't be able to see. Or you can put it in the question box. I'll keep that small in the corner.
Okay, thanks for
I
that.
think the default is muted though, so you can't, like I'm online and I don't have the option to unmute.
Yeah, okay. Oh, I see. Yeah, so folks wouldn't know how to unmute.
Do you have the ability to unmute yourself now?
There's a little bit of a lag, but not seeing it.
I have the option on.
Okay, cool. I hope we don't get anybody
Oh, yeah.
invading our meeting.
Okay. So the lines, the colors are the different caps, and the line type is the catch restating scheme you use. So okay, so I'll start from the case where you have no future climate scenario, so to speak. Is it that biomass is still a little dynamic? It declines a little bit, and we can get into the details of why that happens in a few slides. But you're looking at total groundfish complex level here, right? And there's two things to take home here. One is that applying the stricter caps basically forestalls like it keeps biomass stable for slightly longer. Eventually, three of them end up in the same place by the end of the run, and then the strictest cap of them all instead is still remain higher than the others. In the bottom panel, you see catch, and the second big take home from this slide is that a cap can be constraining for a certain time and then stops being constraining as the biomass and the productivity of the system changes, right? So if you look at the pink line and also the orange one, so the 600 and 400 lines, they essentially they keep the catch below their respective limits for a while, and then they don't anymore. So that's arguably what we have seen in the real system, right, where this cap may have been a representative of the system productivity at one point, and then things changed, and that wasn't the case anymore.
I mean, one of the things that crosses here is that it's 400,000 tons, looks like multi-species at MSY, given the process. So is that right?
They say the 400,000 tons.
Look, when you look at the, obviously the decline is because you're above BMSY for a lot of these things, including origin.
Right.
Right.
Yeah.
So you're fishing, as you go into the future, you're fishing stock down towards, without the no climate scenario, which is not quite static, but it is what it is. You're reaching equilibrium in terms of catch, because in biomass terms, you're reaching BMSY, multi-species BMSY with the particular mixes. And it looks to me like the equilibrium catch, even under the highest cap, is at about 300 and something thousand.
Which is where deadline levels out.
Exactly. So that would be multi-species BMSY under the F35 proxy deal.
Right, except you're not applying control rules to all of these.
Well, but BMSY you wouldn't.
Right.
Unless you end up with some stocks below.
Yeah. Yeah, but remember that some of these are really low fishing rates.
Exactly.
Yeah.
But that's what I'm saying. I'm saying under the scenario of managing the groundfish fisheries and the Fs for everything else.
Yeah.
Total multi-species yield is about 300 and something thousand.
That's right.
So any cap that's way above that is not on average ever going to come into play.
Yeah, so that's kind of where the four stocks that have the HCR, that's like their B40, basically, like they all end up sitting kind of like, and also the other thing is that here there's no noise around recruitment. It's just like there's a stock recruit relationship. So, like if you let this model run for long enough, like eventually those four will end up at around B40, and then all the other ones will be, still fished at fairly low. But yeah, so anything, and we'll get to that to the end, to like how to possibly set on these caps. So the thing that did surprise me was that when we then started doing climate runs, looking at the total groundfish complex, nothing really changes at all. So that's not true, but there's very, very minor differences between these increasing emission scenarios and the one with no climate. And things really change when you start drilling into the single species side of it. So for now, put a pin in that, but at the level of total catch and total groundfish complex, there is some, a little bit of added noise, but for the most part, it seems like the fishery as a whole just carries on through these various scenarios. At least that's what the model says. So another way to look at this, this is the same data, just summarized in different ways. So these are decadal averages for the projection period. These bars are the difference that you have in catch and biomass up at the top, and then revenue at the bottom, compared to the status quo. So if you were to like switch from the status quo that you have now to another one of these cap values, that's, like obviously what you run into, you're leaving catch on the table, so you have losses in your average groundfish catches. You have gains in your groundfish biomass. Of course, you're leaving more biomass in the system. One thing that I thought was interesting here is that the gain in biomass seems to be higher than the loss in catch, and note that that's the same scale on the y-axis. And to me, that means that you're essentially, by not extracting spawners, you're leaving more spawners in the system, right? And obviously the lowest values of this cap are in no way meant to be realistic. So that's an enormous amount of catch that you're leaving in the water. But for the other ones as well, you do have gains in biomass that compound over time until then the caps become unconstraining, and then there's no difference from the status quo anymore. You could, as a simple exercise, take estimates of X vessel prices and multiply those by catch, whatever that is worth. Like when you project so far into the future with a static estimate of an X vessel price, you're probably not really saying a whole lot, because prices change over time substantially. But if you were to take recent estimates of prices for the various stocks, you would see, of course, a fairly large loss in the revenues for the fishery. But yeah, so the biomass gains seem to be bigger than the yield that you left on the table. I'm not really showing here what goes on in terms of the catch rescaling schemes or climate, because at the level of the whole complex, that's not so consequential. It will become important at single species level later on when we get into that. Which is about now, it seems. So okay, so those that you've seen so far are results at the level of the complex, right? So I'm starting from cod, because why not? Because that's maybe the most well, according to the model, the most dramatic, let's say, yeah, exciting. I don't know. But so here you get to kind of see what's going on under the hood at single species level. So you have another multi-plot panel. Here you have the biomass fraction on the left, catch in the middle, and on the right you have the amount of rescaling that went from your harvest specification to your catch based on the cap that you imposed, right? So yeah, so the blue lines up top, there is no rescaling going on at all, because the cap is unbinding, and for the other ones it becomes unbinding as you go forward in the projection. Let's put a pin in the dash lines for a second. I'll start from the biomass fraction. So that's kind of what we were talking about a minute ago. You're starting your run from near B0, and folks that are familiar with Gulf management and Alaska management, of course, cod isn't anywhere near unfished. right now in the Gulf of Alaska. But remember that the reference point that this control rule uses is not the same as the single species one. It's a multi-species reference point. So as far as the HCR is concerned, stock status was fairly high at the beginning of the projection period. And that's just, you know, you kind of have to choose between doing things consistent with the model itself internally or trying to represent the single species dynamics as best you can. And there's a bit of a trade-off in there. So this is where I'm at now. Future rounds may use different reference points, or you could tune the biomass of the cod stock itself, and you would have different trajectories. But essentially, they go and sit near B40 where they can, where you have a cap like the 200,000 that prevents them from doing so. You're well above your B40 reference point.
So value of 1 in 2020 is unfished, not just 2025. Is what you're saying?
Yeah. So basically here the model is saying, so in 2020 is when I first started applying the control rule in the projection. And as far as the control rule is concerned, you know, biomass was at a point that was near the multi-species unfished that you got from those curves. Yeah. And that is going to apply to pollock as well. Whereas I think that in the real world, the cod is at about, cod is on the ramp.
33%.
33%.
So 2% away from the.
Yeah.
I mean, the multi-species status at the beginning is relative to multi-species B0. So this is multi-species B0, not single species B0.
So it's cod's B0 in the sense that it's when cod was at F equals 0, but all the other stocks were also in the model and were fished at some background value. Yeah.
So yeah, you've got to be quite careful when you define
B0.
B0.
Yeah.
Yeah. I mean, the weird thing about multi-species is you could end up above B0.
Yeah.
Whatever B0 is, depending on the predator. You know, there's heaps of predation from arrowtooth and all that.
Yeah, and that's why your B0 is never going to go as, you know, higher than a certain amount, because you have stocks of other stuff that are imposing M2 basically on your unfished cod.
Could I ask a quick question just to understand it better? But does it use near-term recruitment at all, like from the assessment?
For no, there's a stock recruit relationship.
It's just that, no.
It's just that.
Okay.
And so another.
The concept of rec devs does exist, but not in this.
It's just ironic because if you took a near-term period for BMSY, we'd probably not that far from that because recruitment's been terrible for the last 15 years.
Yeah. Yeah. And that's probably why that's where you are, because the model is using a stock recruit relationship. And again, and I forget the specific case with cod right now, but a lot of the Gulf or a lot of the Alaska assessments, there's no estimate of steepness, right, or stock recruit relationships in these models. Like a lot of times you have random recruitment or random devs around mean recruitment. Right? And so there would be another way to do these projections, would be by imposing noise. Huh? Well, that's the problem, right? You can't just pick one set of realized devs for the projection period and just call that. Well, there would be one way to put some noise around it, but
it won't change the mean.
It wouldn't change the mean. It would add noise, and then when you combine that with climate, you may crash the stock earlier, maybe, or later, depending on where your devs ended up.
Remind me, and I should know the answer to this. When you've got a stock proof relationship, what is B0 in the stock proof relationship? Or using the alpha beta parameter?
Alpha beta.
So where's beta from?
So that we did ages ago. We were available. We went to alpha and beta from steepness estimates
And
from
it must be from B0.
and from B0 estimates from assessments.
So how does that affect something like that?
That was the pre-tuning parameterization
Okay.
of the stock recruit relationship. What happens after that is all kinds of calibration to get to an age structure that resembles the age structure that the data is showing you. But right now, if you were to plot those alpha and beta parameters and look at the stock recruit curve, that may not be the same that the assessment says, right?
Right, and that's why I'm sort of intrigued by, so just to, you know, if this is something we want to focus on, you know, this 1.0, what is it? You know, when we tend to think of B0, it's B0 in stock root relationship.
Yeah.
Right, and that isn't going to be this thing.
No.
And that thing is closer to system-wide B0 in some sense.
Yeah.
So it might be interesting to see what some of these look like relative to the stock root relationship B0.
So see what the current stock recruit relationship parameterization.
Yeah, where does it think you would equilibrate in a single species?
Yeah.
It's not fair to do that.
Yeah, and that'll be one way. That'll be maybe the only way of getting something close to a single species B0 from this model.
Right.
Other than turning off a bunch of species, but then
you end up in lower.
then you end up in a model that doesn't really make, you know, much biological sense anymore. So well, yeah, that's kind of where the no climate run is at. But so cod would be one of those cases where climate does matter according to this model at least. So as you go further down row by row, you see the different projections under the various basically think increasingly warm as you go down these rows. And again, you know, applying the cap delays the inevitable, in a sense, for a while at the cost of leaving a bunch of catch on the table, of course. But in the worst climate scenario projections, you kind of converge to the same spot by 2080 or so, 2075, something like that. Even though the HCR tries to close the fishery by 2070, I think, well, you couldn't see my mouse anyway, but by 2070 or 2075 in the worst climate scenario, what's happening there is limitation to spawning, basically. So recruitment failure, in other words, that drives the stock down.
Recruitment failure because of predation?
Hot, still hot.
Survival
Of eggs, yeah, they don't, like the eggs won't hatch. We don't have eggs in Atlantis, but that's how we use those thermal ranges. Yeah. So yeah, and I'll get a little more into what goes on with the climate stuff in a second. One thing that I wanted to show was basically what happens to the HCR shape as you apply these different caps. This is the realized shape of the harvest control rule for Pacific cod, and the leftmost column is the status quo, where you have no cap. At no point there's a cap that is constraining your catches in that case, and that you kind of get to see in the bottom left as stock biomass goes down. You kind of get to see the left-hand side of the control rule. So that's kind of like that 20% HCR that shuts down the fishery when you hit the 20%. The 400,000 cap kind of shows you the whole idea of applying these ecosystem caps and what that does to the single species HCR, and that's been shown plenty of time. But that's basically a way of banking biomass as you get close to B0, maybe even beyond B0 in some cases. You may choose to keep collecting catch at a set amount, or you could keep all kinds of different things to essentially be below the target fishing mortality, right? And then you kind of converge at the target fishing mortality when you're around B40, and then you're on the ramp when you go to the left.
But the interesting thing is it doesn't help you. The banking, it's like putting your money in the wrong bank.
Yeah.
What you're doing is you're adding to mortality, the deaths.
You're adding to stuff to eat for other stocks. Yeah. I didn't go into that. There's a very short time where the banking does something, like a cap allows you to still harvest a bit more than an unconstraining cap, but it comes at a cost of so much that you're leaving on the table before that kicks in, that it's really not, from the standpoint of the catch alone, it's not a good deal. But there's other considerations that I'll show later that,
I find it interesting that the bottom right isn't linear below the E40. With my pathetic eyesight, it looks sort of curved.
Well, yeah. I see what you're
I was
saying.
expecting, I was like the second and third have got really nice kink and stock cruise relationship. But the last one, where you've got heavy climate, you've got a curvature. Any idea why that is?
Well, so when you're at B40, so basically you're saying that you should be in the space of the plot below the original HCR, right? But you still have the cap that is playing there. So that's not the HCR alone. You still have the cap that is still constraining your catches. And so you can't, if you look at the bottom, you're looking at the bottom right. Yeah. So that is the only reason why you can see the left-hand side of that curve is because the stock is going down.
Sure.
Right. Otherwise, you would be in the upper left, the upper right of that multi-pen plot. But you can't all of a sudden, when you're below B40, like go way up where the HCR would want you, because you still have the cap that is keeping your catches low.
And it just ends up as a non-linear relationship on the left hand side.
Right.
Yeah. Is the 200,000 cap constraining before you hit B40?
Yes, it's constraining at all times. Yeah. Except then for cod, I guess it stops constraining cod itself, just because like the fishery closes, period. So the cod stops being in your cap effectively.
Sure. I just wondered what biomass level corresponds to the cap. I guess is it like B30 starts, you hit starting the cap once biomass hits like B30 effectively.
Biomass corresponding to.
So like what does biomass have to be before the cap comes into place? Like if you apply your harvest control.
Well, that's the equilibrium that you showed us.
Yeah. So
Problem with these is
so you would be approximately. It's hard to do on a single species base, right? Because the cap is multi-species, and the cap won't care. So you have two levels of management here, right? You have the single species management, which is what makes this like fairly complicated. Is you have the single species management that looks at your single species stock biomass, and that's all that modulates your single species stock biomass is your single species HCR, right?
Okay.
Effectively, so does the cap, but you can't quantify how it does so. All that you do as far as the cap goes, you can't quantify how it modulates the total groundfish complex.
Let's go to the next slide. That I think gets closer at the single species level where you've got no.
This one?
Yeah. So it's not in biomass units, is it? It's
No, that's biomass fraction.
Yeah,
Which means
biomass fraction. So what you want to know is what is the first column in biomass?
Yeah.
Because, you know, forget the below threes, the rows 2, 3, and 4 are influenced by the climate. But the first one sort of is multi-species deterministic.
Yeah.
And so when you don't see those lines going together, then the cap is influencing the equilibrium. But the others, looks to me like they're all going to end up in the same place. It looks like 40% on something.
Yeah. Yeah. Yeah, and I have the raw biomasses, of course, but not on this plot. Okay.
I mean, the top, just understanding it in B without climate is actually quite, I mean, thinking of this, you know, thinking about what does the equilibrium surface look like, I think is useful.
Yeah.
Before you then start complicating it with trends.
Yeah. All right, I'll pick up a bit here. This is same plot for pollock, kind of same thing going on. So pollock is one of those cases where this model says that there is basically nothing going on climate-wise, and so I kind of dug a little deeper on why not, because we know that I mean, you know, cod is, as far as we know or understand, is a sensitive species, but it's not the only sensitive species, and I did expect to see some effects on other stocks. But so this hopefully kind of helps us understand what's happening here. So what you've seen is total biomass, right, in the previous plots, but you can dig deeper under the hood and look at weighted age and numbers at age and how that changes in the various climate scenarios compared to the case that does not have any climate, right? And this is a snapshot at the end of the run, right? So like after these stocks have been exposed to these conditions for a long time, basically what happens here is that your stock structure changes fairly substantially, although the total stock biomass may look fairly similar. You basically end up with populations that are at higher weighted age, and you know, it could be a think tank of its own to talk about why that happens. Of course, there's not much food limitation going on here, so these stocks basically benefit from this, right? From the consumption curve. You have temperatures increasing. You're kind of like in the ballpark of like below the 10 degrees. This is groundfish, so they care about bottom conditions. So essentially, you're giving them a way to increase their weighted age, and when food limitations come into play, then that's where you run into issues. But that was not really strong in these runs.
So would it be useful at some figure in some supplementary to show for some of these species where with the time trajectory of the average fish is in on? So basically, I know my glasses here, but I should have. But let's take the purple curve, right? Over time, you're moving along that curve.
Yeah.
And it'd be interesting to see plots of, you know, as a function, like you do in the control rule plot. So,
yeah,
you know, obviously you've got a spatial grid, so your average temperature is plot. But it would be interesting to see how far you go along that line as a function of climate, for example.
So plot that scalar basically over time.
Yeah.
Yeah.
Well, I mean, I think it's just coloring the line, because presumably over time you're just moving to the right more.
Oh, I see. Yeah, or that.
But what we don't know is, you do, but we don't, where you started and where you ended up, right?
Yeah.
And so presumably you don't end up on the side of the.
Yeah, no, you don't. Well, you might in some select boxes, right? Because this is, like you said, this is an average at the entire model domain level. But you might have spots where, you know, you ran into limiting, and we know that you do for spawning, for instance, although for cod, really mostly for cod. So it depends on a lot of things, like there's movement going on, and depending on what time of the year the fish are in what box, you may or may not run into a temperature that is a limit or not. But for the most part, if for the purple line, which is arrow tooth, you'll never get
You never get.
past the hump. But
Always
the hump
good
is
for
at
arrow tooth, what is the problem?
the hump is at 12. Well, and you know, these are all from lab experiments. So it's a bioenergetic curve, but the way that that is then translated to the conditions in the real world may or may not look like that curve.
But I just think, given that's what's underlying, just showing.
Yeah, yeah,
what
yeah.
that does that, I think.
Yeah.
Be cool. And I just use the average in the population. because
Right.
Obviously, as they die, they don't experience temperature.
Right. Yeah.
I guess juveniles and adults might well have different trajectories.
Percentage change is positive, no,
Positive until it's not.
So again,
that percentage change is positive, I mean, the percentage change is negative.
percentage change is that's a positive change. Yeah. That's a positive change. As opposed to so what happens to the numbers at age is the opposite, right? And unfortunately, I should have reported that because it gets kind of swamped out by the dark blue from cod, so you can't really see what's going on in the other groundfish species that are here. But
The legend label still says weight of age, is that in there?
oh no, that's an error. Sorry,
That's a
sorry.
feature.
It's a feature. Yeah,
Feature.
you just the bottom plot is numbers at age and AA, not weight at age. Sorry about that, and thanks for pointing it out.
But there's a little bit of red there.
So there is a little bit of red in the very first age class and a little bit the second, and that's because spawning and recruitment are fecundity is condition based. So what you're having is you have an increase in the weighted age at the top. So basically bigger spawners and slightly bigger spawning output that then gets kind of like, you basically have more mortality. And another way of looking at this is you have increased growth and increased mortality is really what's happening here. And the two things together, they kind of at the total biomass level cancel each other out to some extent for some of these, but then you end up with a population that looks pretty different from what you had. So fewer larger fish, and that's at odds in a, well, that can be at odds with a lot of the theory that sees smaller fish in warmer water, which we know happens and is driven mostly by food limitation, which is what I was talking about. You don't have much of that going on here.
But that's what this is saying, is that you're going to have more larger, small fish.
This is saying the opposite.
Huh? I mean, the weighted age is going up.
You're right, but you have few. Oh, I see what
But
you're.
you've got-
Okay, no, I see what you're saying.
Yeah.
You have, but overall you have fewer fish
Right.
in the population.
Yeah, you've got fewer fish in total, and the impact in numbers is at the older age classes. But if you're still around, you're a big happy fish.
If you're still around, you're doing fine.
But I think that's consistent with the sort of theory.
Right.
It's good, individually, it's good to be warm. Population size.
Yeah.
Which is what we saw in the seminar on Friday.
Okay, so that's kind of like what
Very capitalistic.
the what?
It's a capitalistic.
It's like it
model.
is a capitalistic.
Most people suck, and a few do really well.
All right, I think we can skip over this. One thing that so here's where the catch rescaling stuff becomes important. And okay, so this is, what's this? This is the rescaling of your harvest specification that occurs under the various caps. These are only three of the 19 stocks that I have, but it kind of shows you what happens with those catch rescaling schemes, the equal one and the attainment-based one. So the solid lines are where you say that all stocks are equally valuable, and you attain them all in the same way. And if you look at the solid lines across the three columns, they're all basically identical, right? So the cap is doing the same thing across all these three stocks. Where things change is with the dashed line. So basically, where you prioritize attainment of, in this case, cod, at the expense of, in this case, arrowtooth, and pollock is kind of someplace in between these two. Essentially, the model is trying to maximize, you still have to comply with the cap, but the model is trying to maximize the catch of what you told it that you want, that you value, so cod in this case, at the expense of arrowtooth. What happens here is that you then run into spaces where you can't zero out the catch of the stock, because this is a multi-species fishery, so there's going to be bycatch. The model does not explicitly account for technical interactions, so interactions between the fleet. There's no fleets in here, it's just an F per stock essentially. So you got to be careful that you don't rescale the catch of stocks that you deem to be low value too badly, such that then they choke a fishery in some way, right? So there still has to be some allocation.
And we didn't put attainment for arrowtooth. The previous paper, remember, had arrowtooth attainment reduced. Is that down here, or are we fishing at FMSY? It's taking the ABC.
No, it's not taking the ABC. It's fishing arrowtooth at recent F,
Okay.
which is fairly low,
Yeah.
and the cap shrinks it even further.
Okay, that was,
Like,
yes.
you know.
So the control rule really isn't playing a role.
The control rule is not applied to arrowtooth. The control rule is only applied to cod, pollock, POP, and sablefish. And there was a decision just based on the fact that,
It doesn't make any sense to do anything else.
right, like practically, it doesn't seem like it. I mean, theoretically, all these stocks are managed under control rules, but practically, you're never going to be fishing arrowtooth at F target, right? Yeah.
Okay, no, sorry, I forgot one. Sorry.
No.
Like, but I know you had a slide on it, you have to go back to it, but is there an easy way to explain the difference between equal and attainment based?
Oh, yeah, sorry. Okay, so think that you have a cap that is constraining, right? So you have to comply with that cap. The equal rescaling, you're basically saying all the stocks that are under the cap have equal values, and I want to attain them all in the same way. So if you were, you know,
So they're proportional to
there you go. Proportional for all of them.
to history or to the new?
Just to whatever you need to make them at the cap. So the combined harvest specifications exceed your cap, you need to comply with the cap, so rescale them all by 0.8. And so thereby the sum of them complies with the cap. But you're not making decisions on which ones you want to prioritize. There's no prioritization, in other words, yeah. Whereas in the one based on attainment, you just go and say, well, it may be in a way, it attempts to mimic what happens in the real world. Yeah.
So go for the more valuable ones.
Yeah, but not to the point of like a main bank control where you know, pull a card and then have zero.
Right.
There's a way to avoid it going to zero for, you know, arrowtooth, which, to be honest, if you're at 200,000, that's what you want to do.
Yeah.
But the model doesn't let you do that.
The fact that it differs from the other two kind of indicates that it's less valuable.
Yeah, exactly.
Yeah.
And there's a tuning parameter, and I can't remember how I did it anymore, but there was a tuning parameter. You give like desirabilities.
Yeah, so it's you deciding going in, right, which stocks are valuable and which ones are not. The way that we did this here was based on attainment rather than price. So basically we looked at attainment and said, you know, like cod is attained at basically full, historically it's been attained at full attainment, full catch. So that, you know, rank there is your most important one, and then go down. Okay. Okay, we're almost through with the results part. This is an ecosystem model, so it would be a disservice not to at least think about ecosystem level effects. You can kind of do the same line of reasoning with other indicators in the system, whichever ones you think are important. Here you have again your difference between the various levels of the cap and your status quo. So imagine you switch from what you have now to another one of these, what would happen? The top plot is a repeat from earlier, is how much catch you lost, right? So the price that you pay, and then the other three panels are what happens to a couple of different groups, non-target groups or groups of groups in the model. And note that the scales are different in this case. Basically, what happens here is you're simply leaving more groundfish biomass in the system, right? And this is a trophic model, so you have this standing pool of groundfish biomass that interacts in different ways with the other trophic levels, and so there's more predation mortality imposed on things like forage fish, which includes capelin, sandlin, herring, all those species that are managed as forage in the Gulf, and they get eaten by groundfish. I put in there a plot of what happens to halibut. I wouldn't really look at that. So what's that saying is that basically, again, you're leaving more groundfish in the system. That's really mediated by predation on juvenile halibut, mostly from arrowtooth. The scale is very small in the scheme of the whole halibut stock, and that's total biomass. That's not even spawning biomass. Besides, like I said, there's no technical interactions in the model. So in fact, by reducing fishing pressure on groundfish, conceivably you would probably reduce prohibited species catch of halibut. So if anything, I would argue that you may end up doing, well, I don't know that, but you know, that would need to come out in the calculations, how reducing overall groundfish fishing could positively impact halibut in the sense that you wouldn't have bycatch.
But the F halibut is still the same. It's not, because you don't have technical interaction.
No, you don't.
So the halibut we kill is the total kill, not the total landing. Right? So what you're saying is would be.
It's not in the model.
Sorry?
You gotta have halibut mortality in the model.
Yeah.
Halibut catch.
Well, you have a halibut in the model, and you have a halibut F on halibut. But I think that halibut F already accounts for prohibited species catch.
Right, that's what I'm saying. Your kill would be the same. You'd be able to land more.
But if under the 200,000 ton cap, you're fishing much less groundfish, that halibut F would probably be lower in practice, in the real
Or
world.
because the biomass. You're saying.
Well, no, because you wouldn't have incidental catch of halibut. Well,
Right, you just give that catch to the people who.
to the halibut fleet.
Yeah.
Well, maybe.
But I think what it changes how much is landed versus discarded.
Right.
And so, yeah, they do that.
Oh, I see. Yeah, because you can retain.
You can retain, yeah. So my question, having looked at that, is what about salmon? Do you ever output salmon? I know it's sort of brave to do, but
So we
salmon.
don't talk about that.
But because again, they're in the same sort of category. There are going to be trophic interactions. You know, salmon are not going to be affected by lower forage biomass, right? But then they're also going to be impacted by lower predation mortality. So they'd be given how valuable they are, looking at how they change in a relative sense might be interesting.
Yeah. No, that's a good point. I have not looked at salmon.
I know that I'm not sure you want to look at salmon, but.
No, I should.
But it is actually an interesting one because it's at that mid-trophic level that you could get some quite interesting data.
Yeah.
Maybe bigger than the halibut.
Yeah.
Something eats salmon.
Huh?
Something eats salmon.
Oh, yeah. Yeah, so in any case, all of these are basically top-down and bottom-up effects. The one on top predators, I thought it was interesting, which is the bottom one. Again, leaving higher groundfish biomass in the system, there's more food. The way that I frame that is, so now in the next plot that I'll show you, I've shown you time series up until now for the most part. Now you're gonna see kind of like a point in time, like a snapshot in time, where two of the caps are still doing their job, the two lowest ones. whereas the two top ones are no longer constraining anything. And so that's what you see here. So this graph is again a weighted age change from the baseline, except in this case, climate has nothing to do with this. The baseline is the status quo cap. And so of course the 600,000 is the same. It's not binding anymore. So again, these caps only work if they bind anything. But the other two are still binding. And what I see, what my model is saying here is that these few top predators that I picked here that you see on the in the graph across most age classes, basically they're bigger. Their weighted age is higher, and it's not a huge number. It's up to 10-12% for sea lions, I think, but that's fairly substantial. Is my understanding.
The numbers don't change, presumably?
Say again.
The numbers don't change?
No, not much. I don't have it plotted here, but the numbers don't change much, no, because they're not ectotherms, so they don't have any of that spawning stuff going on. No, what goes on there is what changed in the diets. So that is the change in the groundfish proportion of their diets. Again, model output, right? We get to look at.
Never say that. It's true.
No, it's not. We get to see at the realized diets within the model under these various caps, and you know the percentage change varies among the species. Oddly enough, well, not oddly enough, but it just so happens that the one that has the biggest change is one of the species that has no change in weighted age. That's just because we're thinking in proportions here, right? So like the seabirds, they do eat some juvenile pollock, juvenile groundfish, mostly pollock, but that's not a large component of their diet. So 30% change of 0.8 is not, you know, a whole lot in the scheme of things. But there is essentially, again, more groundfish in the water, increased uptake of groundfish is what the model is saying, increased weighted age. So this is an example of one of the things that you can look at with models like these ones. You can kind of like trace or track movements of nutrients through the system and which compartments they affect.
What's the deal with size class, age class 4 for other filaments?
There would be that's the shift from juvenile to adult, and so that's when they shift from they have ontogenetic diets.
Sure.
So that's when they go from juvenile diet to adult diets. You know, it's a cartoon, right? And those, remember, are multi-species, multi-year.
Well, yeah, they're multi-age ages.
Multi-year age classes. Yeah.
But I was expecting a sort of smooth change in color. Sort of from my eye, it looks like it's bolder in that.
Yeah, that's gonna be, my guess is that is gonna be the first age class of the adult diets.
And so something weird and transient happens.
Well, yeah, the diet proportions change fairly substantial. In some cases, fairly substantially, and so just, you know, they just eat different things. And in the real world, it would be a smoother transition, but in the model, it's not. In part because it's just juvenile versus adult diets. There's no transition in between, and in part just because they're multi-year age classes. Okay, we don't need to focus on this. These are some ecosystem indicators that I'm kind of playing with, but I don't think this is worth going into very deeply. It just kind of shows you how, again, this is an ecosystem model, so we're trying to frame our ideas also in terms of how the ecosystem as a whole gets affected, and the way that you pick ecosystem indicators really depends on what is meaningful to your system. We're kind of like some of the more universal / boilerplate ones that you can look at to kind of get some information on the structure of your ecosystem and how that changes over time. So kind of like your ratios from between forage fish biomass and groundfish on the left, or gadids and flatfish within your groundfish complex, or broader invertebrate to, or shrimp to groundfish indicators, and kind of like how they get affected by different cap configurations and potentially climate scenarios. But let's see, maybe the only thing to drive home.
I'm gonna leave you guys to finish the next meeting.
What time is the faculty meeting?
11:30.
Okay. Yeah.
You're actually ready for that meeting.
Okay. So
More fun on that meeting.
I'll breeze through this, but maybe the only thing to showcase in this slide is in the middle panel. Middle column is really one of the few places where your catch cascading scheme has an effect. So basically, of course, if you're prioritizing your flatfish, your gadids catch, you're going to have less gadids biomass in the system. So different cap configurations can be distortive of ecosystem structure. Maybe the other way around is true, that because a more constraining cap gets you closer to an unfished state, the distorted case would be the case that has unconstraining caps, one could argue, but that's maybe neither here nor there. So I'll move on from this slide. And the last thing results are, because there's some discussion that I want to touch on. The last thing that I'll show is kind of like the trade-off spaces that you enter in these multi-species fisheries. So this plot here shows you the trade-off between pollock and arrowtooth biomass. And we know that there is a fairly substantial trophic connection in the Gulf of Alaska between these two, where arrowtooth is a predator of pollock. One of them, but a fairly important predator because it's a large biomass. And so all this is showing is that configurations that leave more unfished arrowtooth biomass in the water may affect your other groundfish biomass in the sense that there's going to be increased predation mortality. So if you look at pollock versus arrowtooth, the trade-off space is kind of like a declining line between the two, right? Where the more arrowtooth biomass you have in the system, the less pollock biomass you have in the system, and that's, like I said, mediated by this trophic interaction between the two. So the decisions that you make as to what you catch and how and in what proportions has effects on. This is a multi-species system, so it has effects on the other species as well. All right, so I better wrap up here. I showed you, hopefully, that applying caps that are lower than the status quo can delay biomass declines, but it comes at a cost of catch and revenue. Maybe the most important thing, if you had to remember one thing from today, is that these caps can become unbinding as time goes by, as conditions change. So these have been set, now 40 years ago or so, and it's not entirely true that they haven't been reviewed. There have been processes that have considered them as part of the fisheries management plan as a whole, but they haven't been changed in any case, and maybe that could be thought about for the Gulf. Some climate sensitive species eventually seem to collapse, sea cod, and you can do prioritization to help maintain high catches of the species that you care about. There's indirect effects on the other trophic levels if you get more groundfish in the system, and there's trade-offs determined by the preferential catch cascading. Let's see, I'll mention some caveats. The list is probably way longer than this. This is a model, like we said. These caps are meant to be bookends rather than realistic values. We don't account for technical interactions or bycatch. These weights, this catch rescaling was not optimized for a specific purpose. Like I said, this was kind of a first step that we had at it, and you might want it's all purpose driven, right? So what are you trying to accomplish in your fishery by using a cap? Are you trying to attain some species rather than others, or what are the motivations, and how is that going to guide the way that you rescale your harvest specifications to get to the catch? We talked about no stochasticity around recruitment. We talked about the fact that this is a deterministic model. So what you put in comes out. So the climate responses depend on model structure and parameters, no food limitation. And when you use ROMs outputs, you're always dealing with one possible future, right? Not the absolute truth of what the future is going to look like. So that's going to affect your model outcomes. So we've been asked, well, I've been asked, so then what's then a value that you should use? And for the cap, if not the status quo, and I don't believe that the intent, well, my intent is not to solve for that with this model, because I don't think that this model can do that. This is not a fully quantitative representation of the real world, but there are things that we can do. I think we can look at the trade-offs that the different caps cause you to operate with. So ask the model, if I apply a cap of X, what happens? And that's kind of what I gather so far. You have some positives and some negatives that you have to put on the scale. So you're forestalling declines and increasing catch stability, more groundfish and so on, supporting predators, but you have a lot of the negatives. And like what, you know, when you put everything on the scale, what it is an advantage of there's an advantage to using a lower cap or not. I think that there's a couple of ways that one could think about an alternative cap. The simplest one is just look at the data, and here I have just catch, but you could look at the harvest specifications or single species estimates of productivity and see where they sit. And if you set, well, anything that is higher than the last 20 or 30 years of catch and harvest specifications is, you know, probably not going to really help constrain much in the future either. One thing that we've done in the past in another paper, we kind of computed multi-species MSY or a proxy thereof with this model. And you can kind of see where that sits at and discounted by some level. So basically the same thing that was done for the original cap. Where that kind of crumbles down is for abundant species that have low attainment. So again, R2 flounder is probably a fairly high contributor to a multi-species MSY, or it would be in if you were to take that approach. But then in reality, it's not caught. So and that's really half of what happens, in my opinion, in the real world cap, is that you have a lot of these low attainment species that were included in the original calculation of the cap, but then they're not pursued. So you're not really constrained in a practical sense, as opposed to the Bering Sea, where pollock alone, like you said, is most of the cap value. So yeah, it all boils down to what is the purpose of the cap, in my opinion, and should it change over time? And if yes, then one might think of reviewing it. But yeah, it's a complex issue. So anyway, thank you. It was great to present. It was a little long, but I'm happy to take questions. I'm happy to take emails later or talk more about any of this stuff. Yeah. Any questions?
Yeah.
Yeah.
Great talk. Just from the perspective of caps in general, just, and I'm curious what Isaac would say about California current experience, if they ever tried to look at that. But compared to the Bering Sea, which is kind of the gold standard for cap use and how it has been called an ecosystem constraint, I think the biggest difference between there and the Gulf of Alaska is you have a lot more constraints. Almost every fishery is heavily constrained by bycatch limits. And in the Bering Sea, we have bycatch limits that are constraining some fisheries like arrowtooth. It's not so much that they're not that great economically, it's that they also have huge bycatch limit constraints for halibut. So you can't, I mean, even if they were the most valuable stock, given the current halibut bycatch limits, it'd be really difficult, I think. And I just wonder, so, well, I have a lot of thoughts, but I don't know, Isaac, you can share anything about California current type stuff, but I imagine it's similar there with some of the constraints that's already in place.
Well, just for the Gulf, I think, I always thought a lot about how to include bycatch and how to have some minimum levels of catch included in those cap rescalings. I think we know it's a complicated problem, and I think that's sort of like saved for the next paper. We certainly have lots of conversations about bycatch and technical interactions and how to do it right. Yeah, I don't know, for the California current, I think the main, the main difference between Alaska and everywhere else is that we harvest many more trophic levels all the way down to, border species in many years. And that's a completely different set of trade-offs and a different type of and yeah, many of the trade-offs that Ali's showed today are different or in opposite directions once you're talking about harvesting sardines, squid.
Yeah, thanks both. I agree. I mean, they're two very different systems. Even the Gulf and the Bering, right, with very different fisheries and constraints. And it's not like there aren't other constraints in the Gulf already, right? And I don't know that the answer is. One legitimate question I think could be, does there need to be a cap at all? Because there is one in the Bering Sea. I don't think that is an argument alone for having one in the Gulf of Alaska, right?
Yeah, I guess so.
Yeah, and I mean that's a very complex socioeconomic question, I think, rather than just the ecological side of it. And I don't know that. I mean, I know that halibut is a huge bycatch concern in the Gulf as well. I do not know of which fisheries, if it's also specific for, I mean, I assume flatfish trawling, I would imagine.
I wouldn't call it a concern, it's a constraint.
Constraint.
It's taken into account, it's negotiated. It's, it's not like it's a concern that it's not counted. It's a constraint on all the other fishing.
Because the mortality, the incidental catch mortality goes towards the total halibut mortality, right?
Yeah.
Yeah.
You got a hand up.
Yeah. Do we do Isaac?
Yeah, just briefly to say, the work that you're doing now, adding in the fleets explicitly, I think might be one step towards that. Thinking about bycatch more carefully. And then also, I just wanted to ask, so you showed those nice plots of the ecosystem trade-offs, like changes in weighted age of mammals and birds. I wonder if it's worth digging into those sorts of plots for, also for the groundfish that are included in the cap that we haven't really talked about. So if I remember correctly, you have skates and thorny heads and other species, because some of the motivation for the cap is that just generally in the literature is that caps might help you manage species that are sort of, to which you can't allocate a lot of assessment resources, you can't allocate a lot of quantitative resources, but you might get some bang for your buck by taking this sort of more cautionary consideration of overall productivity. I don't think you've done that yet, but it would be interesting to see what the
Yeah.
trade-offs are for this skates, thorny heads, grenadiers, I forget.
Right. Yeah, and no, you're totally right. And it's, we tend to always look at the key three, four stocks, but there's a lot more than those. And when you look at total biomass of the whole complex, those are big contributions. And we don't get to do, well, I don't know if it's in part, I guess it's a data limitation, in part it's just kind of like there's no need for, full complex assessments on regular basis for some of these non-target stocks, but you're right. I think the whole idea, like, well, not the whole idea, but one strength of the CAP approach would be to address species that you don't have an assessment for. And I think that there are assessments for skates and all that, although they're not maybe as, like they're certainly not the same tier as stocks like polo cod and those.
They're included in the cap.
They are included in the cap, but I don't look at them much, and I should.
Yeah, there's a question online. Robert, would you like to go ahead?
Hi, thanks for sharing this. And I'm working with Isaac on the California Current Atlantis, and I sort of just kind of want to return to this idea of the fact that a lot of this is in reference to a baseline or like no climate scenario. And it seems like even in that scenario, these caps aren't really coming into play. So I'd be more interested to kind of see just what's going on in like your baseline or no climate scenarios before interpreting kind of how it's affecting other things. Like, for example, our climate, or like not even the climate-based model for California Current takes about 75 years to sort of balance out. And I know you talked about that a little bit with kind of your time series, but do you have an idea of when yours balances out in the non-climate scenario?
Yeah, thanks for asking that. That is a great question. So what I didn't show in those time series output is that there is what we call a burn-in period before 2020. So essentially a period of time where I give the model a chance to cycle through instabilities and equilibrate, not quite equilibrate. If I were to wait for the model to really truly sit at equilibrium, that would be a comparable time frame to what you mentioned, so 70 to 80 years. But those 30 are enough to get rid of, like, shed off the first kind of cycle of big instabilities in the diets and in the age structures to get the model to a stage where they realize the age and size structures resemble real world conditions. However, the other thing that goes on there is that at year 30, so year 2020, you have the HCR kicking in. And in that case, it doesn't matter how long you allowed your model to equilibrate for. If you're starting to, so basically you have a big jump in your fishing mortality essentially at year 20, and then from then on, depending on where the stock was sitting biomass wise, it will try to converge towards B40. So the short of this, it was kind of long-winded, but the short answer is that it's hard to get rid of non-stationary dynamics in these models, as you know very well, I'm sure. But some of them are inherent to the model. Some of them are, not by design, but they're a product of what fishing mortality does and when you start fishing down your stock and where it was with respect to B40, if you do apply a control rule. But yes, I don't know if that answers. But yeah, the case with no climate is kind of like the benchmark that we look at.
Right. So to clarify, you're saying that you're applying an HCR starting in 2020. So that's like introducing another instability. So I'm wondering if you just have that HCR applied throughout even your burn-in period, then you might be able to, you know, get a little bit closer to a more stable baseline to compare. But thanks for the detail.
Yeah, no, that would be an option for sure. If you could do that, and then at the end of the 30 years, you would be 30 years ahead of the curve, closer to B0. Sorry, closer to B40, not B0.
Thank you. And if I can, just one more follow-up question, really digging into those weighted age and numbers at age. You're kind of comparing to baseline values, but what baseline is that? Is that the no climate, no cap scenarios, or is it like climate paired baseline essentially?
Yeah, thanks. The short answer is the baseline is no climate, no cap. So that's what this plot says. That's just compared to the status quo with no climate scenario, and so was the other one for the groundfish. So the baseline is the case that you're applying as few of these forcings as you can.
Okay, yeah, that's something we're struggling with. Of do you compare to a baseline of no management changes, but still the climate effects, or do you compare back to like a pure baseline? So you might get a different story.
That's true, you would, and that's why it's important to pick your, what your baseline really is. But we should follow up. I'm happy to chat about this more offline, Robert.
Yeah, absolutely.
Thank you.
Thanks, Alvin.
Thank you,
Thanks,
Alfie.
And we're up.